Okay, recalling that the velocity of the center mass is the same as the velocity you would have after collision if the collision was completely inelastic, and that's given by this expression, which is easily derived from the basic principles. Now, big idea, and I'm not proving this at this point, just giving you an overview, but in the center of mass frame, an elastic collision is characterized by the fact that the after collision velocities are equal and opposite to the before collision velocities within that frame. That means that the velocity of this object, as observed from the center of mass frame, the velocity of this object just reverses. And the velocity of this object just reverses. Now, it's easy to move from one frame to another. This is very convenient. All you have to do is keep your wits about you and add or subtract the right velocity to each of the velocities, and you're going to get the right result. Okay, so we can write that as v prime 1 relative to the center of mass is negative v1 relative to the center of mass. v2 prime relative to the center of mass is negative v2 relative to the center of mass. So let's go ahead and apply that to a problem. Okay, here's a 2 kilogram object moving at 6 meters per second and a 4 kilogram object. That's a bad choice of numbers. I'm going to let this thing move at 9 meters per second. The reason that's a bad choice of numbers is that would have given us equal and opposite momentum. Center mass frame would have been stationary. Wouldn't have been very interesting. Wouldn't have illustrated what we're trying to illustrate here. Okay, so the application, well, first of all, the velocity of the center mass frame, use capitals here so we don't mistake that as a centimeter. Velocity of the center mass frame is going to be m1 v1, which is 2 kilograms times 6 meters per second minus plus a negative 9 kilograms times 4, negative 9 meters per second times 4 kilograms, can have negative 4 kilograms, divided by the 2 kilograms plus the 4 kilograms. And that equals what? Well, that's 12, and that's negative 36, so that's negative 24 kilogram meters per second. Divided by 6 kilogram meters per second, which is equal to then negative 4 meters per second. So what we do, if this is an elastic collision, now if it's a completely inelastic collision, of course, that's going to be our final velocity of the system consisting of the two objects stuck together. But if it's elastic, if the collision is elastic, these two objects are going to move apart with the same total kinetic energy they had originally. And this is going to hold. So let's just look at what V1 center mass is, capital M, equals what? Okay, the center mass is moving this way at 4 meters per second. The first object, if we take this as the first object, let's call this M1, let's call this M2, so we keep that straight. Okay, here's the first object. It's moving at 6 meters per second this way. The center mass is moving toward it. Now, there isn't anything at the center mass, but the center mass of this system, the balancing point, is moving in this direction at 4 meters per second. So what's the velocity of this mass going to look like from an observer that's moving this way at 4 meters per second? Let's go ahead and just, center mass is going to be closer to this mass than the other. So let's just do a little fulcrum here to indicate the center mass. And indicate that, as we found here, the center mass is moving at negative 4 meters per second. Okay, well, relative to that moving center of mass, this velocity is plus 10 meters per second. That's obvious. We can, of course, get that by subtracting the velocity of the center of mass from the velocity of the object. So that's V1 minus V center of mass. And I'm not going to write down all the numbers. That comes out to be plus 10 meters per second. And velocity 2 with respect to the center mass is what? Now we can reason this by common sense. Center mass is moving at 4 meters per second. This is moving in the same direction at 9 meters per second. So, and I guess I should have called that negative 9 meters per second. So, this object is overtaking the center of mass at a rate of 5 meters per second. So from the center of mass, this object is approaching it at 5 meters per second. That means it's moving in the negative direction at 5 meters per second. So we'd better get negative 5 meters per second when we do the calculation. Well, okay, let's do the calculation. That's going to be V2 minus velocity of the center of mass. And what's V2? Negative 9 meters per second minus negative 4 meters per second. And that equals exactly what common sense tells us. So there's the entire calculation. Okay, so might have trouble finding enough board space to finish this. What's that tell us? Okay, back to this principle. The velocities in the center of mass system reverse. So velocity 1 after collision is going to be negative 10 meters per second. Velocity 2 is going to be plus 5 meters per second relative to the center of mass. So that V1 prime relative center of mass has to be negative 10 meters per second, and V2 prime relative to the center of mass is going to be plus 5 meters per second. So that V1 back in our original frame, okay, this object is going to be moving now at negative 10 meters per second relative to the center of mass. So it's going to be moving this way as viewed from the center of mass at negative 10 meters per second, but the center of mass is moving at negative 4 meters per second. Pause and see what you think. Now, I'm going to say it. The velocity of the first mass then is going to be negative 14 meters per second. So in the original frame, V1 equals negative 10 meters per second minus 4 meters per second equals negative 14 meters per second. V2 equals I forgot to put the primes on these. This is V1 prime center of mass. So no, never mind. I'm not as tuned in today as I'd like to be. Okay. Then V2 is going to be relative to this. I was looking over there and don't know why. Okay, so relative to the center of mass, the second object will be moving at plus 5 meters per second, meaning the center of mass is going to see the second object approaching it at 5 meters per second. Excuse me. so that in this frame, how is something going to be approaching the center of mass at 5 meters per second? Well, it's going to have to be moving more slowly than the center of mass. And well, you're going to get V2 equals 5 meters per second minus the velocity of center of mass, 4 centimeters per second, equals 1 centimeter, 1 meter. Per second. So this slows to 1 meter per second, moving this way at 1 meter per second. The center of mass receding at 4 meters per second. And something's wrong with that. Let me pause for a second and straighten this out. Okay, this is right. I was just saying this, I kind of, in my mind, reversed the positive direction and something didn't seem to work out. The mass M2 will be moving in this direction at 1 meter per second. And these are the velocities after collision in the original frame. So let's be careful that this is V1, this is V2, this is V1 prime, V2 prime. So this mass will move off at 14 meters per second this way, and this one will move back this way at 1 meter per second. Now let's just check this. What's the relative velocity of these objects before collision? It's 15 meters per second. That should be clear. 6 meters per second this way, 9 meters per second this way. We're going to get to 15 meters per second. What's the relative velocity after collision? Well, now this object is moving this way at 14 meters per second. The second object moving this way slowly at 1 meter per second. And the relative velocity is now negative 15 meters per second, as observed from the position of the first mass. I just said that wrong. The relative velocity is plus 15 meters per second, as observed from the first mass. The first mass sees the second object moving that way at 15 meters per second because it's moving at 14 meters per second, second object moving at 1 meter per second. Now we can check to make sure momentum is conserved, and we can check to make sure kinetic energy is conserved by this process.